I think of it as the sort of spectrum of methods from optimization to machine learning. So at one end of the spectrum is methods that entirely separate optimization and learning entirely. So this is predict and then optimize separately. So you can think of this as that we start by training a machine learning model. The model sees a loss function that quantifies how accurate it is. And then once the model is finished training, we plug the results of that into a solver for the optimization problem of interest, right? And these parts of the problem just don't talk to each other. And so the challenge with this approach is that there can be a misalignment between accuracy as measured by the loss function and whatever the end goal of this process actually is, which is typically making good decisions, in some sense quantified by an objective function. At the opposite end of the spectrum is what we might think of as a pure end-to-end approach. And so here, maybe instead of having the sort of machinery of optimization and all of that, I just have a giant machine learning model, and it maps directly from whatever the inputs of the problem are directly to the discrete output of interest. And so we're going to try to learn away the structure of the problem entirely. And so this might seem appealing, that it allows us to train in an entirely end-to-end fashion. But it involves the problem of teaching neural networks how to solve discrete optimization problems, which they're typically not very good at, right? Like they don't reason naturally about this kind of structure. And so this tends to be very difficult to make work in practice. And so really what I want to pose is that these two extremes are really extremes on a spectrum, right? And that we can sort of interpolate between them in terms of how much weight we place on sort of the hard-coded optimization components of the system and how much we introduce learnable parameters, right, that allow sort of adaptation in particular ways. And so this talk is going to try to explore that spectrum and introduce methods that get some of the best of both worlds properties, right, in different settings. So here's the specific outline for the talk. I'm going to start out by talking about differentiable optimization methods in the discrete setting. So very much picking up from Brandon and Priya's talks, but then thinking in combinatorial optimization and how we make that work. Then I'm going to talk about a couple of other families of approaches that are based on either, in the second part here, transferring sort of more of the heavy lifting to the learning component by learning how to map optimization problems onto simpler surrogates, right, that are easier to solve or differentiate through. And then finally, I'll mention briefly at the end of the talk a sort of more recent sort of nascent line of work where we try to replace optimization entirely with a learned loss function that captures some of the essential properties that we'd like to still use to supervise the model with. So diving into the first part of the talk here. So I'm going to start out here with an example. So we're going to talk about the class of linear programs. And so here's an LP in standard form. And we're going to think about our setting as where we're predicting the cost vector, right, theta, right? So that's maybe being predicted from contextual information that we use to decide on the objective function on any specific day. And so the previous work that we've seen so far focuses on differentiating mostly the solutions of strongly convex optimization problems. And I emphasize strongly convex here because although LPs are, of course, convex, there's no curvature to the objective, right? It's just a linear function. And then that introduces problems for differentiability. So here's a kind of simple example where we can sketch out the feasible set as this shaded polytope. And now the objective function that we're predicting is a vector pointing in some direction. So now visually, the optimal solution to the problem is the vertex that lies furthest in the direction of that vector. But what that means is that if I perturb the objective function by even an infinitesimally small amount, my optimal solution can hop discontinuously from vertex to vertex. And this is a symptom of the fact that the Hessian matrix is singular, right? So all of those terms that we want to deal with in the KKT system are sort of ill-conditioned. And so this poses problems, right? Fundamentally, the thing that we want to differentiate through is not differentiable. And the question is what we do about that. So this first class of methods seeks a differentiable proxy to the underlying non-differentiable object that still hopefully communicates important information for the model to have in the backward pass, right? So even if it's not exactly the task of interest, it's still conveying some sort of smoothed or approximate sense of how the decisions that you're going to reach will change as a function of the predictions that you're making. And it turns out that, at least for LPs, we can do this in ways that don't require too much heavy lifting beyond what you've already seen so far. So we can just smooth out the LP relaxation in a way that will guarantee differentiability, essentially by adding basically any strongly convex term to the objective function here. And so in this piece of work, we chose the two norm of the decision variables. which kind of smooths out some of those corners. And you can show that this gives us some of the things that we want, that the solutions become differentiable in a sort of nicer way, and that the distortion that we introduce, right, is bounded, right? There's this parameter gamma that controls how much weight we put on that regularizer, and that trades off between smoothness and fidelity of approximation to the original discrete problem. Yeah, and then the implementation is literally just plug this into any of the tools that Brandon talked about, and it kind of works. So I'm going to talk about one class of applications here, kind of illustrating these methods. And so this is an application taken from healthcare where we're dealing with tuberculosis treatment. And so tuberculosis requires a long course of antibiotics. Typically, even first-line treatment is about 6 months of daily antibiotics. And so one of the challenges, of course, in administering care in this setting is adherence to treatment, right? People stop taking their antibiotics at some point for any of a variety of reasons. But that causes problems downstream, right? It causes relapses, or it causes the development of antibiotic-resistant strains, all sorts of things that we'd like to avoid. And so oftentimes there will be programs where health workers visit patients to try to keep them in treatment, but that's a pretty high-cost action, right? In the worst case, it means actually showing up at someone's home, which you can't do very often. And so you have limited resources. And what we'd like to be able to do is to predict which patients are at greatest risk of non-adherence, and then optimize the assignment of health workers to try to keep as many patients in treatment as possible. And so in this specific application, we used data from the city of Mumbai, provided by a nonprofit called 99 Dots, where we're exactly doing this, where we're using past adherence to predict future adherence to medication, and then solving an optimization problem that we formulate as a matching between health workers and the locations in the city to visit. And here we're going to compare two different approaches. One is this two-stage approach where we separate prediction and optimization. And then the second is what we call a decision-focused approach, where we backpropagate through that matching problem, right? So we put the differentiable proxy for the assignment problem into the training loop of the model, and then use as the loss function the quality of the schedule that it induces, right? How many patients who actually need an intervention you would have in fact visited. And so here's a kind of similar figure that Priya showed you, where we have these two different axes for comparing the models on. One is what we defined as the objective function, which is the number of missed doses of medication that would be caught by a health worker in 1 week on average. And here we find that the decision-focused approach has a reasonable advantage, right? It results in about 15% more of these successful interventions, even though when you evaluate the models via the AUC here, right, just their binary prediction accuracy, the story is reversed, right? It looks like the two-stage approach is doing substantially better. And I think this reinforces the sense that really how you measure the performance of models matters a lot, right? Especially when the prediction problems are difficult and all models are far from perfect. Really, what you tell the model it should be looking for has a substantial impact on what you get out of the process. So that's linear programs, but LPs are, of course, a pretty special case, right? They're an exact relaxation that then you can just add a smoothing term to. And so the question is, whether this works in any sort of more general setting. What do we do when we have more difficult combinatorial problems? And so here I'll mention just one example of this, which is mixed integer programs. And here, this takes the LP formulation, but then adds the constraint that the variables have to be integral. And so this dramatically changes the character of the problem, right? It becomes extremely expressive, but correspondingly extremely non-convex, hard to solve. And the question is whether you can still differentiate through the mixed integer program in this sense. And so here, the idea is that for classes of problems that can be solved via a cutting plane solver, in fact, you can use sort of similar machinery. So a cutting plane solver basically successively adds constraints to the optimization problem in order to prune away non-integral optimal solutions to the relaxation, right? So you keep adding additional hyperplanes that separate out these sort of like false optima and successively tighten the LP relaxation. And so what this suggests then is that you take the original LP relaxation, which in the worst case might be very sort of loose and uninformative, and then you add additional constraints to it, right? Like you run the cutting plane solver in the forward pass, you get additional cuts that are added, you add those as linear constraints, and then you can plug this into the sort of differentiable LP framework, right? You backpropagate through this now tightened LP relaxation. And this turns out to work well in practice for a variety of domains, even if you don't solve the cutting plane problem to optimality, right? Like you get sort of better performance just as you add more cuts that make the relaxation more informative. So that's one sort of class of methods that sort of somehow try to make discrete optimization differentiable. Yeah.
Can I ask a question now, Brian? I can wait.
Yeah, we can do questions.
So in this previous method you just described, like once you add this regularizer, even if you were to add like the ideal cutting plane formulation, are you guaranteed that you'll get a binary point?
No, you
get something on the interior.
Yeah, that's exactly what it's doing. It's like shrinking the solutions like a little bit into the interior, so that there's like a smooth surface they can vary on.
And then how do I interpret that, like in the actual problem of interest? Like,
So
do you think of this like a randomized solution, or do I have to? Is it very domain specific how I then interpret this binary point?
Yeah, I think the interpretation is pretty domain specific. I think like there are domains where you can think of it as a probability distribution over solutions, but then sometimes in those domains, like you can do a little bit better by like working with the domain specifically, right? Because that suggests like a specific kind of relaxation. So for example, we worked on some modular optimization, right, where there's a multilinear extension that's exactly a probability distribution over solutions, and you can sort of work with that directly.
Cool. Okay, thank you.
Yeah.
What about the case of degeneracy, where like multiple optimal solutions exist for your binary problem? Aren't you like more or less with the regularization term, aren't you more or less like then doomed that you always like stay basically that you fall in the middle of like across the different optima?
Yeah, so the question is if you have like many like nearly optimal solutions, right, of similar value, and then yeah, the regularizer is just going to pick one, right? It's going to, in this case, it'll pick the minimum norm one, and I think that's basically okay, as long as there's some consistency from iteration to iteration, right? That as you make updates to the machine learning model, you're okay basically picking the same local neighborhood to stay in. But if that breaks, right, that then suddenly you really wish that you were in like a different neighborhood entirely, right? Then maybe that would start to cause problems.
No, I was more thinking of the case like where you basically then land in some kind of LP optimum that is like where every binary variable has like maximum functionality that you can't.
Oh, I see. Yeah.
But probably not with the regularizer.
Yeah, so I would view that then as a symptom of like turning up the regularization parameter too much, right? And yeah, you probably need to move a little bit closer to the discrete solutions then.
So in the previous example, when you actually solve the problem, you actually use the MIP to solve the problem at the end?
Yeah, exactly. Yeah, at inference time, it's all, I mean, because then you need the actual discrete solution to the problem. So you just run the solver. Okay, so now we'll move on to the second class of methods here based on learning surrogate solvers. So far, kind of all the methods that we've dealt with have had the basic form that in the forward pass, you run a potentially sort of relaxed solver for the optimization problem. And then in the backward pass, you differentiate through that relaxation. And that works for a lot of problems, but there's also problems where this becomes cumbersome to deal with, right? Either because we don't sort of have, very natural relaxations, or just because of the computational cost, right? Like these methods that want to propagate through optimization oftentimes end up requiring cubic time in the number of decision variables. And there's ways that you can try to leverage special problem structure to do better than that, but sometimes the scalability just becomes really challenging. And so the classes of methods that I'm going to present now try to leverage additional learnable components of the system in order to simplify optimization, right? So we'll still have optimization in the loop somewhere, but we're going to do more kind of pure processing, basically via the machine learning part of the system first, in a way that we hope reduces the complexity of the optimization that we have to do later. And so the way that we can think about this is that instead of this picture where we have the machine learning just like feeding into the optimization algorithm, we're going to have a surrogate optimization problem that might be defined even over a different set of decision variables, and that will have some additional, learnable components to it, right? There will be additional parameters in the system, and then afterwards, we'll read off the solution to that surrogate problem as a solution to the original optimization problem of interest. Here I'm going to cover a couple of different ways of doing this. The first based on reparameterizing the existing optimization problem, and then the second based on learning and mapping to a new optimization problem entirely. So the motivation for this first class of methods is the observation that oftentimes groups of decision variables in an optimization problem take values that are highly sort of coupled or correlated. So this is a kind of extreme example of a shortest path problem. So suppose I'm planning a route from S to T. Then depending on how I set the costs on traversing the edges, I'll always either take the top path or the bottom path, right? There's no other option. But what that means in terms of the individual decision variables is that x1, x2, and x3 always take the same value, right? They're either always all 1 or all 0. And similarly, the values of, for example, x1 and x4 are perfectly anti-correlated, depending on how I set the costs. And so really what that means is that there's somehow fewer degrees of freedom, right? And the effective values that the decision variables can take. And the motivation for this method is, well, maybe we could be doing optimization in that lower dimensional space then. So even if there isn't this perfect correspondence, we could hope that if there is some sort of typical relationship to, between the different decision variables across different values of the parameterization of the problem, that I could just learn a reparameterization of the problem into some lower dimensional space, and then optimize over that lower dimensional set of decision variables. And then this buys me advantages computationally, because if I have, for example, cubic scaling with the number of decision variables, being able to reduce the dimensionality is really good, right? That buys me large computational savings very quickly. So the way that we instantiate this is to learn effectively a projection of the optimization problem into a lower dimension. So you represent the set of decision variables as a lower dimensional vector y here, which we can think of as these meta variables that we're optimizing over. So the intuition could be that you just have a variable that's whether you take the top path or the bottom path, and then a matrix P that captures that sort of projection down from x into y. And so here P is a learnable parameter of the problem, right? And we're going to learn it just by back propagating through the optimization problem itself. And so effectively, instead of having to sort of hard code what we think the right abstraction of the problem is, we're learning that structure as part of the process of training the model with this now additional set of parameters. So here's an example application of this to a class of problems called network security games, where the idea is that you have a graph with a set of nodes that are designated as sources and targets. An attacker is going to try to travel from one of the source nodes to one of the target nodes. And then a defender would like to place checkpoints on the edges of the graph to try to interdict the attacker. And so here's an example graph where the source nodes are triangles, the targets are stars, and then the edge colors are shading basically the amount that different edges participate in different components of the y vector. So the way to read this is all of the red edges basically correspond to one entry of y. So when you select that entry more, you're effectively selecting all of those different edges, right, in proportion to the amount that they're shaded. And the kind of interesting thing here is that the solution, I think, kind of makes sense, right? The different colors here are effectively different ways of separating the sources from the targets in ways that use more or less disjoint sets of edges. And so then you can say, instead of optimizing over the individual edges, I could construct, in this case, a randomized strategy for the defender that just randomizes over those different sets of edges, right? And I'll do just as well. And now this representation is learned sort of entirely by the model itself, right? Without us kind of hard coding some intuition about selecting these disjoint sets of edges. Quantitatively, we also find that this can give you significant advantages in some domains. So particularly when solving the forward pass or solving the backward pass is computationally costly, right? The scaling in the number of variables is bad. Then this can offer much faster runtimes, right? Because you get that sort of cubic improvement from being able to scale down the dimension of the optimization problem. And interestingly, we also find that in some domains, this offers improved performance measured by the loss that you get, right? In terms of the downstream quality of the decisions. And this, we think sometimes can happen because basically doing learning or optimization in lower dimensions is easier, right? Maybe, sometimes you get a nicer training landscape for your model, or it's easier to generalize, right, from a smaller amount of data because you're effectively, reasoning about fewer things. So sometimes you actually get a little bit of an improvement in performance as well. So now I'm going to talk about the second approach here, based on, Angela?
Sorry, quick question.
Yeah.
Is there any comparison to sketching or dimension reduction from Johnson Lindenstrass for the or is it completely different? Your way to compare it?
Yes, the question was if there's a comparison to sketching or doing like a random like Johnson trust thing to reduce the dimensionality. So I don't remember if that is in the paper exactly. I'm trying to decide if this is comparable to like looking at the value at initialization of P basically, right? Like when P is just a random matrix, and that doesn't do particularly well, right? I think like there is, I mean, I think like going back to the intuition, right? Like you don't think that just sort of like random combinations of decision variables are necessarily the right thing, right? Like there are specific variables that are more highly correlated. So at the very least, I think you can probably get away with like a smaller number of dimensions if you kind of optimize over the projection. But it is, yeah, it's a good question. We should look kind of more systematically at that, I think. Great.
I guess I'd be curious, like your intuition as to how expressive you felt that the learned surrogates were, with like in comparison to the original problem, like if there were certain sets of solutions that you were basically now like not allowing, and how much you feel like that mattered in certain areas.
Yeah, so the question is how expressive the learned surrogates are there families of or are there solutions that you can just never reach? And I think that that's true, right? Like there are, like if you look at this example, right, there are lots of solutions that now you just cannot represent, right, with this matrix. And in fact, it's a pretty restrictive family. And I think that there is maybe a question here about kind of like robustness to changes in distribution or something like that, right? Like you've learned something that works really well for this problem setup, right, like for the specific graph structure and all of that. But if you moved one of the sources or the targets or something like that, like I would not expect this to still perform well at all. So maybe there is some question about like trade-offs basically when you want more expressivity.
Is there an implicit assumption that the constraint matrix is fixed? So if there's no distribution over instances in terms of the A is also a distribution, the A and the B have to be fixed?
So I think in the
network doesn't change in the application.
Yeah, I think so. If you're willing to backpropagate like through the constraint structure, then like in principle you might be able to do something, but I would expect the performance then to be like very domain specific, right? Like there are domains where the constraint structure is very different than like there just is no single good parameterization right anymore for what that projection looks like.
Give a few more examples on surrogates. I just can't think of like so right now the surrogate is path instead of the edit. Can you give another problem?
Yeah, sure. So another experimental domain in the paper was like a portfolio optimization problem on stocks. And so there, like you can think that depending on your beliefs about like which way the market will go, you'll buy like one bundle of stocks or another bundle of stocks, right? But like you don't. Like there's combinations of stocks that you would be unlikely to buy together under any scenario. Okay, so moving to this sort of next class of methods here. So now instead of sticking with the existing optimization problem and learning this kind of lower dimensional representation for it, we're going to try to learn a mapping to a different optimization problem entirely. And here the idea is that we're going to think of this as basically like learning a relaxation of the problem in a form that we know is efficiently differentiable. So effectively learning a mapping from the original problem of interest onto a simpler surrogate problem. And the setting that we instantiated this in was for a class of optimization problems on graphs. And the starting point for us thinking about the problem was the sort of the intuition that clustering is kind of like a recurring heuristic for how you deal with like some reasonably broad family of problems on graphs. That you're going to figure out how to cluster the nodes of the graph, and then you're going to use that information somehow as the starting point for building your solution. And that of course has widely varying performance. There's not a lot of problems where like somehow just doing clustering is the optimal thing. But it's at least a starting point of what a good inductive bias for our model might be, right? Like it might want to be able to do clustering like reasoning in order to solve the underlying problem. And so the way that we instantiate that is to learn how to map these kinds of different families of optimization problems onto an instance of a clustering problem. And in particular, we start with the original discrete structure of the problem, right? The input graph. And then we feed that through a model that produces an embedding of the nodes of the graph as points in our And this can be a graph convolutional network or whatever your favorite thing is these days. And then we take that learned embedding and we run it through a soft version of a K-means clustering algorithm. And that algorithm then outputs a soft clustering of the nodes of the graph into different clusters. And then we interpret that clustering as a solution to the original discrete problem of interest. So for example, if we were doing facility location, we could say that our solution is going to be to locate facilities at each of the nodes that are closest to the centers of their respective clusters. And the key step now is that we're going to backpropagate through the clustering to update the embedding model itself, right? So even if this wasn't like really a good idea, just sort of for an arbitrary embedding, we're effectively going to learn a representation of the continuous space here, such that clustering becomes an effective heuristic to solve the optimization problem. And so this is kind of instantiating what I mean by placing sort of more of the heavy lifting on the learning component of the system. Right now, the learning component has to come up with the representations such that this relatively simple optimizer does what we want it to do. And this has a couple of advantages. So one is that for the soft version of K-means, we can get a provably close approximation to the gradient in time that now has much better scalability, right, with a number of decision variables, in this case, the number of nodes of the graph. And it also allows us to learn a relaxation which really adapts to the properties of a particular data distribution, right? So that now we can sort of exploit, the sort of special things that we might encounter in a given application.
Quick question. But you know the input graph is on the left side of your diagram of the flowchart. You know that graph, or is this like implicitly given and you're given probably optimization problem over that graph?
So we look at a couple of settings. One is where the input graph is explicitly given. So this is in the setting where you're basically using this as an optimizer, right? Like it's just like, oh, I want to solve a facility location problem. So the input is the graph and then the output is the solution. And we also look at a kind of link prediction setting where the graph is partially observed, right? And so you have this kind of hybrid of a learning problem of reconstructing the graph structure alongside optimization.
Yeah, I was basically just thinking that if you're given the input graph, you could also simply use a simple graph clustering algorithm, right? Without the overhead of probably using, I don't know, providing a learned embedding, right? And then using soft K-means.
Yeah, well, so you can absolutely just run clustering on the graph. But there's no real reason to think that clustering provides like an excellent solution to any of these optimization problems by itself, right? Like it'll give you something, but it's probably not like really tuned to solving facility location problems. Okay. So then, okay.
Quick question. So this seems to be well adapted for graph problems. I'm not sure. So does this generalize? Like more general and discrete problems?
So, I mean, the short answer is no, right? Like we did this for graph problems because we had an intuition about what works on graphs and, specific classes of optimization problems there. I'm very much interested in kind of exploring the underlying idea, right, of like using continuous representations of discrete objects and then like a simpler surrogate problem. But I think part of the trade-off that we're making is that surrogate problem like really should be somehow related to the optimization problem or something, right? It should provide like a useful form of reasoning. So it's not going to be like fully general across domains.
Question on that. You're doing backpropping, but so you provably close gradient approximations and gradient approximations to what?
To the gradients through the soft clustering layer, right? So that's a gradient describing how the cluster outputs change as a function of the embeddings, like the points of the nodes in Rn. Okay, so I think in the interests of time, what I'm going to do here is skip through some of the kind of like technical stuff about the gradients.
You can go till 2:50. You can manage your time.
Okay. Yeah, I think we can still save a little more time for questions too. And I'll just show quickly kind of wrap up the section with an application, this time in the kind of like learning to optimize setting, right? So we're just going to take an input graph and see how well does this system produce a solution to the optimization problem compared to kind of expert designed algorithms for the problem from the existing literature. And what we find is that, so we look at two classes of problems. One is a community detection problem where we're maximizing a modularity, which basically measures the fraction of edges that lie within communities on the graph, which of course, you would sort of expect is kind of related to clustering somehow. And indeed, like a lot of the expert designed algorithms are doing like a spectral clustering or something like that using specific matrices defined on the graph. But instead, we're going to learn that representation. And then the second is a facility location problem, right, where we have this different interpretation of the facilities as picking out like the nodes at the centers being the facilities that you should select. And in both domains, we find that we get improved performance, on these distributions of graphs that we train on. We get improved performance compared to the expert designed algorithms, right? Because, presumably we can adapt to this kind of like non-worst case examples of graphs. And we're also able to do it, much faster than the kind of hand-designed algorithms, right? So we're able to train extremely quickly because we have this sort of fast approximation to the gradients, and then get an orders of magnitude speed up over having to run the discrete solver from scratch.
So what is the expert here, for example?
So the expert here, so in the community detection setting, it's a combination. So we compared to several things. There was, so these kind of like spectral clustering algorithms that I mentioned, right? So they look at the spectra of some matrix on the graph, and there's different choices for what that matrix is, and then cluster the nodes according to that. And then there's also sort of recursive or hierarchical kinds of partitioning algorithms that will build like more of a discrete clustering to start with.
Is the E2E the method from the beginning, the one where you had the strongly complex?
Oh yeah. Sorry, I didn't mention that at all. So the E2E here is not a method from any other part of the talk. It's just like take a stack of graph convolutional networks and have them predict the optimal solution, right? So like no optimization component to the system, just a machine learning model that predicts the values of the decision variables.
Can we also try your method, another method, where you just solve the LP relaxation instead of the IP? But I guess you also need the penalty term as well.
Yeah.
Or is it?
Well, so in this specific setting, then it's sort of not clear what that layer would be doing, because we're giving it the graph as input, and we know what the optimization problem that we're solving is. So from the perspective of like a differentiable LP, like there's not like really clear parameters that you would be learning there.
But it's an IP, right? So you don't, or is there?
He's not trying to predict data.
Yeah, so we also have a different setting where maybe this would apply, which is the link prediction setting that I mentioned. So there you would have then the input sort of coefficients in the IP being predicted basically as a function of what links you think are present. We didn't try that basically because it seems terrible. That because now you're predicting n squared things, which are all of the different edges of the graph, and then you're trying to feed that into a differentiable IP. And maybe we should try it, but it's like it would just not perform well at all.
You can also interpret predicting the links as basically when you're predicting the constraints. If you don't want to consider the full graph, but essentially you're predicting the links, then the links in the IP become part of like which constraints you have. That's the source code. And the previous method doesn't apply to predicting constraint matrix.
Okay, so now I'll take a few minutes and I'll cover the kind of high level of the next the final piece of the talk, and then pause for questions again. So here the idea is to kind of replace optimization entirely with a learned loss function. So the way that we're going to view the setup that we've been in so far is that the optimization problem is really inducing a loss function, right? It's the loss induced by running the solver for the optimization problem and seeing how good the resulting decision is, measured with respect to the true parameterization. And so far, the way that we've tried to work with that is to look for a differentiable surrogate for the optimization problem itself, right? To replace that component of it. But we could instead try to kind of take a step back and just somehow approximate the loss function that it induces directly, right? Not the sort of mechanics of how you get to the loss function. And the high level way that we try to do this, and this is in some recent work, and Sanket, who's the lead author on this, is here, so you should find him if you have any really hard questions, is that so you look at the underlying loss function and you take samples from it, right? So you can just sample points around the sort of true optimal value of the parameters, and then just approximate the loss function from those samples, right, in the neighborhood of the true value. So you'll get this kind of impressionistic, hopefully kind of smoothed out version of what the loss function is. And then maybe if you feed that into your machine learning model, right? Like if you train the model against this, you can make better things happen depending on how you picked the family that's representing the loss function here. And so when we think, and so formally this works by just by perturbing the optimal, or the true value of the parameters with Gaussian noise to get that set of samples, and then fitting a local approximation to the loss function in the region of each training data point. And so the kind of key question here to make this work is how you represent that parametric family of loss functions that you're going to fit to the samples. And here, the motivation for what we propose is to capture a few what we think of as desirable properties for a loss function in this setting. So one of these is to capture that different dimensions of the parameters might be more important, right? Like there might be some coefficients that just aren't that important to predict really accurately, and others that are, right? That's one reason why we might think that optimization in the loop kind of works well. Another is to capture pairwise interactions between entries of theta, right? So there's been some recent work kind of pointing out that there's sometimes, correlations, for example, matter in stochastic optimization. And so just getting the marginals right by themselves are not necessarily sufficient. And then a final property is that we might want to capture something about asymmetry in over versus under predicting, right? That maybe it changes your decisions if you over predict, but not if you under predict, or vice versa, right? So one direction is more important than another. And so we start out by looking at a family of quadratic loss functions, so it's just going to be a quadratic function of your difference from the true value of the parameters. And then you're going to learn that matrix describing basically like the norm that you're measuring the difference with. And here in particular, we use like a low rank positive semi-definite decomposition of that to reduce the number of parameters that we're learning. And so this gets you part of the way there, right? It allows you to capture the differing importance of different dimensions of theta because the matrix can just put more weight on some entries than others. And it allows you to capture pairwise interactions, right? Because you're taking all of the pairwise products here in the errors. But it doesn't capture any asymmetry in over versus under predicting. And so the kind of final version of this that we propose is a directed version of the quadratic loss, where every individual pair of coordinates gets a loss that depends on the direction of the errors, right, for both I and j. And so, so you have basically like 4 copies of these parameters for your loss function, and then you take whichever one applies for the case for a given pair of coordinates, and that helps capture that kind of asymmetry in the direction of errors. And we find that this gives you reasonably competitive performance on several tasks. So these are 3 different tasks, and then comparing to both a 2-stage approach and a decision-focused approach here, which is which is doing differentiable optimization, right? So differentiable, surrogate like the LP relaxation being smoothed or whatever is appropriate for the problem. And we find that this kind of surrogate learned approach typically performs, on par or a little bit better, despite the fact that it's now not back propagating through the optimization problem at all, right? Like we only have to be able to solve the forward pass in order to get the samples to learn our loss function. But once we've done that, our loss function is now just this relatively simple function that we can evaluate in closed form easily. And so the training process becomes a lot simpler and smoother. And so this is at least some evidence that we can find families of loss functions that allow us to capture enough of what we need about optimization without actually having the optimization problem in the loop at all. So that's it for what I want to talk about today. I think the kind of takeaway for me is that really there is this kind of spectrum, right, between purely relying on optimization and purely relying on learning. And there's, I think, a lot of points that we just haven't even explored in that space entirely. And so really there's a lot more to do. And I think that's part of what makes this area exciting for me, to really trace out that sort of full interaction. So now I think we have maybe a few more minutes for questions. 5 minutes. Okay.
Two questions. For the community detection, did you also compare against the two-way method?
So I don't want to tell you the right thing. I will double check and talk to you later.
Because usually that's quite fast. It may not be the best.
Yeah. Looping is usually quite fast. We compared to several things. I'll just have to double check. Yeah.
I think someone wants to compare maybe. The other question is that for optimal problems, like some problems are hard and some problems are easier and some are easy. Like did you sort of try to look at spectrum of hard to easy instances to see how that works?
Yeah, that's good. So the question is whether we tried to look at a spectrum of hard to easy instances. So we looked at different distributions of graphs, but I think it's a little bit difficult to like boil that down into a summary of how hard the underlying optimization problem is. So that might be something to think about more, right? Like how to characterize like the hardness of a distribution of instances, right? Because it's not just one instance, right? It's a distribution of graphs that you're training or testing on.
There's a bunch of work on something called the phase transition.
Yeah.
Yeah, so you have a model which can generate you different graphs from phase transition, easy ones, and
Yeah, that's true. That would be interesting to look at. Yeah, I mean, I think
that's not a problem.
Yeah. So I think like part of the challenge in setting this up is that like a lot of the phase transitions, at least the way that I remember, are kind of on like random graphs, right? And like then like as you vary the parameters of the graph, right, a phase transition appears. And so I think that'll get us some instances, but it's difficult to define on graphs that you might encounter like from real applications as well.
All known networks are also random graphs of special structure.
Yeah, I mean like very, very special structure. Yes.
But this is random.
So the last part with the approximation, the quadratic approximations.
Mhm.
So those are not necessarily convex problems. So how do you computationally solve those?
So fitting the, are you asking about fitting the loss function or training the model on the loss function?
No. So fitting it, I think is okay. So yeah, afterwards, yeah. How do you optimize?
Stochastic gradient descent. That it's true, like in that sort of last family, right? Like we've lost the convexity of the underlying quadratic functions, but empirically it still seems to work reasonably well.
And then like for the same model, like you said, you have to sample the neighborhood of the true theta. I said this, like the dimension of the true theta and like what the neighborhood of the true theta is matters some material, right?
Yeah, definitely. I mean, I think like depending on how you're scaling is in like dimension of theta versus other operations that you could be doing, right? This is not the right method for all cases, for sure. Great.
Yeah, so it seems like if the velocity of the last project taken to the extreme could be, right? Like, so in the end-to-end predict and then optimize setting, we're basically saying we don't actually care about the prediction being accurate in the way we would care about those prediction, we care about the end-to-end performance.
Mm-hmm.
And it seems like the philosophy taken to the extreme is we don't actually care what the decision-making procedure is either, right? We just care about having some kind of intermediate representation such that the end-to-end workflow works well. Would that be like a correct characterization of the philosophy of the work? That in some sense, you don't care that either the prediction or the optimization part are good, but you care that the end-to-end part is good.
So I think that's part of it. But I also think of part of it as capturing, like those questions about whether you could have just hand designed a loss function that somehow captured like what you needed to for optimization, right? And I think you're right that it's really hard to hand design those functions in a convincing way. But the thought was maybe if we make it a little bit more expressive, that we would be able to learn something that like maybe we don't need the full sort of structure of the optimization problem. There's just particular pieces of it that are important for the loss.
So in clusternet, if I interpret it correctly, you're essentially differentiating through a tablet, the K-means cluster tablet. So my question is, does that pose any challenge to training? Because in training a neural network, usually there's parameters throughout of it. So here you have initial parameters, and then there's a lot of operations that need to differentiate through.
Yeah, so the question was whether in the clustering setting it's difficult because you need to differentiate through all of the kind of steps of clustering, basically like this algorithm. So that's a good question. It's kind of what I skipped over, basically. So we don't actually unroll all of the operations. So we differentiate just through the last set of updates around the optimum. And then you can show that approximates basically the gradients through a fixed point condition, right? Because there's a fixed point condition where the cluster centers don't change between iterations, and that's when the algorithm converges. And you can show that you can kind of approximate that fixed point gradient without having to, either deal with the implicit function theorem or, unroll everything.
Okay, let's thank Bryan Wilder.